So let's see one more example of using changes of variables and Jacobians to transform regions in the plane and then compute integrals. So this problem says let R be the region bounded by the square with vertices 0, 1, 1, 2, 2, 1, and 1, 0. Let's go ahead and draw that. So you have, let's say 1, 2, and 3 here, 1, 2, and 3 here. The first vertex is 0, 1. Then we have 1, 2, 2, 1, and 1, 0. So we have this square. And one thing to notice is that this square is formed by these lines. So we have the lines here, we have y equals x plus 1, the line with slope 1 and y-intercept 1. Then this looks like y equals x minus 1 because its y-intercept is minus 1. And then we also have y equals 3 minus x. The y-intercept is 3 and the slope is negative 1. And this one looks like y equals 1 minus x. So we can use these relationships to find a nice substitution. So if I solve each of these, if I get x and y on the same side and just the number on the other side, the relationships that I find here are that y is equal x minus y equals minus 1. That comes from y equals x plus 1. And y equals x minus 1 gives us x minus y equals 1. Then we also have x plus y equals 3. That comes from y equals 3 minus x. And x plus y equals 1 from y equals 1 minus x. So it seems like we can choose to let u and v equal x plus y and x minus y respectively. And then we have a transformation. So as we did last time, we'll need to solve these for x and y. So it looks like u plus v, that's going to give me x plus y plus x minus y, and that's 2x. So 1/2 of u plus v is x. What about u minus v? That looks like x plus y minus x plus y, which is 2y. So 1/2 of u minus v can be my y. So I'll make this substitution. And I want to remember that u is running from 1 to 3, and v is running from negative 1 to 1. So if I draw now my UV plane, what I've done is transformed the region R, which was this diamond-shaped region up here. This is the region R. In the UV plane, we said that U was going to run from 1 to 3, and V from negative 1 to 1. So that looks like that should be from 1 to 3 on the U-axis. From 1 to negative 1 on the V-axis. I keep putting them in the wrong place. -1. So this rectangular region here. So I transformed it into a simpler region to integrate over. The last thing that I have to think about is my function f of x and y. But it looks pretty nice because x plus y is showing up and x minus y is showing up. So I'm going to say this should be u squared times sine squared of v. Then I need to multiply by the absolute value of my Jacobian and integrate over s. So let's write that down below. So integration over s means that I want to integrate from -1 to 1 in terms of v, and from 1 to 3 in terms of u. And as I said, I have u squared sine squared of v. So I'll compute my Jacobian and integrate du dv. Jacobian, I need del x, del u. So if x is 1/2 u plus v, then del x del u is 1/2. I need del x del v, which is also 1/2. Then I need del y del u, 1/2, and del y del v is minus 1/2. So I'll find the determinant of this matrix, which should be minus 1/2 times 1/2, minus 1/2 times 1/2. That's minus 1/4 minus 1/4, minus 2/4 is minus 1/2. So absolute value of that is positive 1/2. So finally, the integral I want to find out is integration -1 to 1, integration 1 to 3, u squared sine squared v times 1/2 du dv. Since I'm first finding my antiderivative with respect to u, I can treat v as a constant. I can also pull 1/2 out in front. So this becomes 1/2 integration -1 to 1 sine squared of v times u cubed over 3 and evaluated between 1 and 3. And that's going to be dv, of course. So when I plug in my upper bound of 3, I get 3 times 3 times 3, but I'm dividing by 3, so I just need 3 squared. That's 1/2 integration -1 to 1 sine squared of v times 9, which is 3 squared, minus 1/3. But that's just a constant, so I can simplify it and I can pull it out. So this should be 27 over 3 minus 1 over 3 is 26 over 3. So I can say I have 1/2 times 26 over 3, which will obviously simplify. We'll do that in the next step. Integration from -1 to 1. Sine squared, I'm not sure of the antiderivative for that. So I'll go ahead and do 1 minus 2 cosine of v, 1 minus cosine of 2v, I'm sorry, all over 2. And integrate with respect to v. So I'll pull out this 2, this 1/2 from inside the integral. I'm also going to cancel here and get 13, so I have 13 over 3, and it becomes 13 over 6 when I pull out the 1/2. 13 over 6, integration -1 to 1, 1 minus cosine of 2v dv. And that's not bad. I can say that's 13 over 6. Antiderivative of 1 is v, and antiderivative of minus cosine of 2v should be sine of 2v over 2 maybe minus sine of 2v over 2. And we'll evaluate between -1 and 1. So I have 13 over 6. And that's going to be times 1 minus sine of 2 over 2. And then minus, I'll evaluate at my lower bound, -1 minus sine of -2 over 2. So that should be 13 over 6. 1 plus 1 is 2. And then I have minus sine of 2 over 2. But I know that sine is an odd function, so this term here, the sine of -2, is going to become the minus sine of 2. Minus times minus is plus, so it becomes plus sine of +2 over 2. So those two terms cancel. Final answer then should be 13 over 12. So you might have noticed I made a little tiny sign error there, a couple of steps before the end. When I evaluated at my upper bound of 1, that's here, then I need to subtract evaluating at the lower bound, so this should have been a plus because it's minus times minus. So that means that when I use the odd function property, I just get minus, so 13 over 12, and then minus sine of 2. Minus 13 over 6 sine of 2. And that also shouldn't have been 12, because that would have given me 3 there.